Okay, our third presentation is parameters affecting the performance of the 12G performance of digital patching systems by Dr. Dimitris Antsos. As manager of the Space Communications and Navigation Technology program at NASA's Jet Propulsion Laboratory, he is leading a group of technologists in the research and development of state-of-the-art technologies for the future of spacecraft telecommunications. In addition, over the past 20 years, he's acted as a consultant to companies in the broadcast switching and patching industry. In that capacity, he has designed and developed advanced high-bandwidth switching jacks for patch bay applications. Dimitris.
Thank you for the introduction, John. My name is Dimitris Antsos. I'm a microwave engineer. I have been a consultant in the audio, video engineering, and broadcast area for the past 20 years or so, most of them in a very fruitful association with BitTree. I'd like to also acknowledge and thank Ari Baron and Brian Carpenter, who are in the room today, who were helpful contributors in this work and in this paper. I'm going to talk about parameters affecting the performance of 12G digital patching systems. So without further ado, let's talk about the transition to 4K and UHD and all kinds of other neat new formats which are very data hungry. And I claim that this transition requires single link 12 gigabit per second serial digital interfaces for the routing of uncompressed video. There are several disadvantages to doing so over existing 3 gigabit, fourth quad link 3 gigabit, including increased hardware complexity at source and destination, patching system size, cost and complexity, inefficient use of existing patching resources, and the fact that the serializer, the receiver, must synchronize the 4 separate transmission paths. Some time ago, some of you are not old enough to remember that, but the fast connection between a computer and a printer was the parallel port. And those days are long gone, and we've moved over the past 10 years. The electronics industry has moved to SerDes, serializer, deserializers, for precisely that purpose, right? For taking parallel data, moving it to serial. Why serial? Because the crosstalk problem between different lines in a big parallel data bus doesn't exist anymore, and because you don't have synchronization problems between the individual data lines, so latency issues. And so we clearly need to have that infrastructure straightened out for 12 gigabits per second. However, 12 gigabits per second introduces much higher frequencies of operation, which then are prey to the ill effects of reflections, of losses, both conductive and dielectric, of frequency dispersion, and the ill effects of that, and as a corollary to that, single mode propagation. So I'm going to address some of these issues here in my presentation next. Okay, so the question becomes how do we define reflections, and what is their representation in the time domain? So as you will see here, a 4 dB, this is a mask. The mask shown here, the red curve in my graph, shows the return loss or reflection coefficient specification by the different SMPTE standards as they came online for the different bit rates. So 292 for 1.5 gig, 424 for 3 gig, 2081 for 6 gig, and finally now 2082 covering 12 gigabit serial data interfaces. And so what you see here is the fact that a 4 dB return loss as allowed by the SMPTE 2082 standard from 6 to 12 gigahertz results in 40% of the power, the incident power, being reflected. So an effective insertion loss in your serial transmission of 2.2 dB, which is certainly not negligible. However, the question is what parts of the frequencies of the different parts of the frequencies of the signal, what reflection coefficient do they all see? And so what I've plotted here is the power spectral density normalized to 0 dB for a 3G signal, a 3 gigabit per second signal. And there's two versions of it. There's a fast version and a slow version. So the fast version, or the slow version, has a rise time of 225 picoseconds, which is the maximum allowed by the 424 standard. But the reality is that many line drivers that the industry implements in transmitters are much faster than the minimum, the maximum rise time, have a much faster response, which is a good thing, as we're going to see later in the presentation. And so I've also plotted the power spectral density with respect to frequency of a fast rising 1/10 of the maximum allowed by the standard here, the power spectral density of such a signal. So this is an NRZI, non-return to zero inverted signal, such as is used for SDI transmission. And so what you can see is what's expected, right? That the power of the fast signal, which is the green curve here, is spread much further out in frequency than the slow signal. So what does that mean for us? Well, what it means is that for the slow signal, about 99.8% of the power lies in the main lobe, and 90.7% of that signal would see at 15 dB or better return loss, and 9.1% of the power, the total power, the part that's between 3 and 6 gigahertz, would see, 1.5 and 3 gigahertz, would see as bad a return loss as 10 dB. So that results in an effective insertion loss as seen by our signal, our SDI signal of 0.17 dB. Things are much worse for the faster signal, however. The faster signal has 1/10 the maximum rise time allowed by the standard and is more in line with commercially available line drivers. For that signal, the effective insertion loss is 1/4 of a dB. So it starts going up, and let's remember, all of us, that this is just still only a 3 gig signal. Now, what happens if we move to a 12G or a 12 gigabit per second signal? Well, now 99.8% of the power still is in the main lobe for the slow signal. Now the maximum rise time allowed by the SMPTE standard is 75 picoseconds, and 93.9% of that power sees better than 7 dB return loss, but a full 6% sees as bad a return loss as 4 dB, which is the return loss allowed by the standard between 6 and 12 gigahertz. And so therefore the effective insertion loss rises to 0.57 dB, and things are even worse for the fast signal. So if you had a signal with rise times 1/10 of the slow signal, which is the maximum rise time allowed by the standard, the effective insertion loss seen by that signal would be 0.74 dB. Now you might say, well, that's only equivalent to 3 or 4 feet of coax at 6 gigahertz, so what's the big deal? I mean, is that something we even need to worry about when most of these systems, the transceiver systems, work with between 20 and 40 dB of total loss between transmitter and receiver? And the answer is yes, it sounds a little bit innocuous if you look at it only from a frequency domain-centric viewpoint. But there's also a time domain analogy to all of these reflections. So the question is, what shape do these reflections take, and where does that power go, and can it create ill effects in your transmission to your video picture received, and artifacts in that picture? So let's take a look at that a little bit more. And now let's view reflections in the time domain. So in order to illustrate some of these examples and these ill effects, I measured 2 3G well-regarded industry standard Normaling mini Weco jacks with BNC connectors that were patched with a 2-foot patching cable. And I had data between DC and 5 gigahertz. So you can see from the data here that my measured reflection coefficient almost meets the SMPTE standard 2082 mask, at least up to 5 gigahertz or so. I mean, we have a little bit of higher reflection here, but not much. And what I did is then I extrapolated these S parameters. This is measured S parameters. I extrapolated them all the way from 5 to 12 gigahertz, assuming the worst case SMPTE reflection loss mask as shown in the previous chart. So I assumed the minimum return loss specified by 2082-1, and I assumed a square root of frequency insertion loss dependence. So I did some simulations in the time domain of NRZI, non-return to zero inverted input signals, to see what the reflections would look like in such a system that, in fact, followed the SMPTE standard. And so what you see here is the result of these simulations. First, I did so for a 3 gig signal, 3 gigabit per second signal, with the maximum rise and fall time allowed by the standard 424, which is 225 picoseconds. So you can see that fact by the gentle rise time here in transitions between bits here. We have a fairly noticeable slope. This is not close to a vertical situation. And you can see that the reflected signal, which is the red curve, has an amplitude, peak-to-peak amplitude of about 100 millivolts, which is not a huge portion of the 0.8 volts peak-to-peak that's the output of your transmitter. However, things become much more serious when you take the faster rising signal that we talked about, which has the 1/10 the maximum rise fall time allowed by the standard of 22.5 picoseconds. So you can see that at the transition points that are now much more steep and vertical, you can see a very pronounced peak-to-peak reflection that can reach all the way up to about 0.5 volts peak-to-peak. So things are getting more serious. And moving forward to now a 12 gig signal through the same system, and remember that with my extrapolated data, this would be a system that would in fact meet the allowed reflection loss mask allowed by the 2082 standard. You can see what you would expect, namely that even for the slowest rise time allowed by the standard itself, which is 75 picoseconds, we have a very large reflection. But if we allow, if we do much better than that, about an order of magnitude better than that, and allow for 7.5 picoseconds rise time, then you can get about 1.3 volts, 1.4 volts peak-to-peak reflections. And so the question is, what happens to those reflections? I mean, you have a patching system, you've patched your patch cord in, and all of a sudden, this energy goes back towards the transmitter. So, as I said, the reflected pulses head back towards the transmitter, and they would ideally be absorbed there if, and that's a fairly big set of ifs, if the output impedance of the transmitter was exactly 75 ohms and the characteristic impedance of the interconnecting cables was also exactly 75 ohms, or at least the two were matched to each other, and if there were no such thing as the structural reflection loss of the cables themselves, and if there were no other impedance discontinuities in the system. But in reality, of course, a lot of these things, these conditions will not obtain, and so you will get further reflections from those reflected signals back towards the intended receiver. And so, depending on the phase lengths of all these cables that interconnect the transmitter to the receiver, you can have a constructive combination, the worst case scenario, of all these reflections and very large interfering voltages at the input of your receiver, which can in fact cause decoding errors and large image artifacts. So my conclusion is that if you want a robust system, yes, meeting the 2082-1 return loss spec is a good starting point, but I would recommend that we go further than that and try to design for at least a 10 dB return loss, DC to 12 gigahertz. So do better than that to give ourselves some headroom and give ourselves a little bit more latitude relative to the vagaries of the architecture of our system. Now let's talk a little bit about power dissipation and loss. So where does the power go? So far we've been talking about reflections. Now I would like to switch the discussion to transmission. So after all, that's what we're interested in, is what gets through, right, to the other end, to the intended receiver. So where does the power, where can we have loss in the power? Well, there are 4 modes of input to output loss, and they all translate into an insertion loss. Reflections we just discussed and talked about, but we saw that at least from a frequency domain standpoint, it's not a huge concern. You can have maybe an effective insertion loss due to reflection of a dB or 2, at least for a single jack system. But I mean, the more the jacks, the more the reflection loss. Radiation, I'm going to assume, is negligible for our systems. They're well-guided, closed systems. You wouldn't expect to lose much in the form of an antenna, in the form of a transmitted electromagnetic wave. But there are 2 very important losses that we cannot ignore, and those are conductive losses and dielectric losses. So conductor loss is ohmic heating of the conductors. Dielectric loss is due to the dipole moment of the electronic cloud inside the dielectric that jiggles around and has a photon interaction between the atoms of the dielectric, the nuclei, and the electron field, and creates heat. But the question is, what's the relative importance of the different loss modes? Well, what I've plotted in this chart is to illustrate that for the same system that I've already shown you the reflection loss of, I have plotted the loss you would expect. The blue curve here is the loss that you would expect out of this system is if the total insertion loss of the system were due to just plainly the reflections. And then the red is the true insertion loss that I measured of this system, the 2 patch jacks with a 2-foot patch cord. And so if you subtract the 2, you can see that the black is a very important part of the loss, and that would be ascribable to the other, the dissipative losses, so the conductor loss and the dielectric loss. So, and of course, this is only for a 2-foot patch cord. If we talk about a 100-foot patch cord or something, or something like that, then most of the loss would be due to, in fact, dissipative loss. So therefore, these factors of loss, 3 and 4 here, conductor loss and dielectric loss, are very important to understand and control. Let's talk about coaxial systems. I have here 2 equations for coaxial loss, both conductor loss and dielectric loss. So the units here are decibels per meter. And so these are the 2 formulas. And I don't want to get too mathematical about them, but I do want to point out some salient features of the formulas. And so what can we do about conductor loss? First of all, the most important thing is the conductor loss is proportional, as we know, to the square root of the frequency. So the higher we go in frequency, the higher it becomes. And so at 12 gigahertz, it's at least twice as bad as it is at 3 gigahertz, right? Because it's a factor of 4 in frequency up. Now, how do we deal with it? Well, A here is the radius of the center conductor of the coax. And so by making A larger and sigma A, the conductivity in Siemens per meter, larger, and so you will perhaps have seen in catalogs these days silver-clad center conductors. Why? Because sigma sub A, the conductivity of silver, is larger than that of copper and gives you an advantage there, so it decreases the conductor loss. What do we do about dielectric loss? Well, the most important thing about that is proportional to frequency, not square root of frequency. So at some point in frequency, as we go up, it will become the dominant mode of loss. And that has several issues about it that I'm going to address. What would we want to do? Well, we can make this denominator larger. B is the radius of the outer conductor of the coax, the shield. Well, first of all, we don't gain much by making it larger because of this logarithm here. Secondly, going larger in size has issues with frequency dispersion that I'm going to address down the line in this presentation, and so we don't want to do that. But one way that manufacturers address that is by reducing this term, which is the relative dielectric constant of the material. So PTFE, polytetrafluoroethylene, when it's gas injected because of the air pockets inside the dielectric, its relative dielectric constant goes down, and so that reduces this term, which reduces the loss. This is the dielectric loss tangent of the material. As I said, at high enough frequency, the dielectric loss will dominate. How high is high? Well, for gas-injected PTFE coaxial cable, some of the best ones that are now available in the market, that transition doesn't happen until 600 gigahertz. That's good news. But that doesn't give us a free get-out-of-jail card. No, we still have to pay attention to that because there are several patching systems and jacks that inside are built out of PC boards and microwave substrate materials. And so if you take the same transition frequency for Duroid, which is a well-regarded Rogers dielectric material, which is filled PTFE, that transition barely happens at 5 to 10 gigahertz. And so if we are going to use substrates and PC boards inside our jacks, we have to be very cognizant and careful of that. Now, how do receivers deal with loss? Well, they assume that the total loss is dominated by conductive loss and is proportional to the square root of frequency. They wouldn't work well otherwise if that assumption is violated. So the question is this a valid assumption at 12 gigahertz? So to demonstrate that, I fit, this is a particular coax cable made by Belden. This is data right out of the data sheet that I called out of the manufacturer's data sheet, and I did a fit of both these equations on this manufacturer's data. And as you can see, this red curve here shows you the dielectric loss, and this green curve shows you the conductive loss all the way to 12 gigahertz. And so you can see that most of the loss, about 25 dB of it, is due to conductive loss, but there's about 4 dB that's due to dielectric loss. And that's what I just said. 25 dB is about conductive loss. So 12.4% of the total loss in a coax cable like that is dielectric. Is that enough to affect an adaptive equalizer to make it not be able to do its job because of the component of proportional to the square root of f? The answer is no. That's the good news. You can see that I fit just a square root of f curve, which is what the adaptive equalizer basically does at the receiver. And you can see that it's still a very good fit. And but at the higher frequency, we have a residual, an error of about 1.2 dB at 12 gigahertz. So it starts to become a big contributor. It starts to become a substantial contribution, but it's not yet big enough that it would mess us up, at least for a coaxial cable. However, that would not be the case, as I said, for if you had a PC board inside your jacks for any reason whatsoever. So we still have to be cognizant and careful of that. Now, another time domain parameter that we need to be cognizant of is group delay and frequency dispersion. So group delay is a key time domain parameter that tells you how long a narrowly circumscribed set of frequencies about the center frequency takes to get from the input to the output of your system. The reason that's important is because you want all the frequency components of your input signal to reach the output at the same time. If they don't, they're going to recombine at different phases, and you're going to have time domain distortion of your output signal at your output. You can also have, discontinuities in the transmission line cause the electromagnetic energy to spread into higher order propagation modes. And each propagation mode has its own group velocity. And many of them, many of the higher order modes, do not propagate with a constant group velocity, like the lowest order mode, which is the TEM, the transverse electromagnetic mode. And so, therefore, that causes frequency dispersion, which causes an out-of-phase combination of the different frequency components of your signal, which causes a distorted output signal. So discontinuities, as I said, in your transmission system, in transmission line, cause reflections. And reflections, because they create trapped signals that bounce inside your system and then leak out, small amounts leak out, and combine with the main part of the signal at different phases, they can also cause group delay variations. And that's illustrated by this measurement very clearly. You can see here that this is the same return loss curve that I showed for the system. So this is the reflection coefficient on the right axis. On the left axis, I have plotted the group delay, and you can see the very clear correlation of the peaks and valleys in the reflection coefficient and in the group delay. And so there are two mitigations, two things we can do about minimizing group delay variation so that we can have a true time delay output of our input. And minimize impedance variations by watching distributed inductance and capacitance. Distributed inductance and capacitance, or inductance and capacitance per unit meter of a transmission line, determines the impedance of the transmission line. So wherever there's discontinuities, there's changes in the cross-section of the transmission line, we have to design in such a way that we change the local properties in such a way that the ratio of inductance to capacitance remains a constant. And so that's one thing we can do. And to ensure the single mode propagation, we want to operate every transmission line well below the TE11 cutoff mode. TE11 is the next electromagnetic mode above the TEM lowest order mode that propagates in coaxial cables. Here you can see some very popular components in coaxial systems and their second mode. So here I'm showing a 75 ohm BNC connector, and you can see two different chambers of the BNC connector. This is the male on the right, the female here is on the left. The cutoff frequency of the TE11 mode in this cavity here is 22 gigahertz. But the cutoff frequency here in the dielectric that holds the center pin is barely 18 gigahertz. And we don't want to go as high as 18 gigahertz. We want to operate about at a maximum, rule of thumb is the maximum frequency of 85% of this 18 gigahertz. So at 12 gigahertz, we're starting to get close to the TE11 cutoff frequency of the higher order modes. Here's a mini WICO connector. Again, you can see that we're okay in the area where the male, the center pin, mates with the female, but where the dielectric holds the center pin, the cutoff frequency of the higher order mode is barely 15 gigahertz. So 12 gigahertz operation would be iffy for this connector. It might spread a lot of power in the higher order mode and therefore create group delay variations and distortion in the output. So I wanted to create some simulations that show just how distorted that can get. And so what you can see here is the classic I pattern, right? The I pattern shows you, it superimposes a number of bits like this. So the input is the blue curve here. This is a 3 gig signal. And the output is the red curve. And I have plotted different bits of the red curve on top of each other to see how open this I is. So the higher, the more clearly open this I is, the more unlikely that the receiver will make an error. Also, jitter is, so this transition here is called the alignment jitter, and that's an important parameter that affects how well the receiver is able to synchronize to this received signal. And so there's a maximum allowed jitter by the standard of 67 picoseconds, and for this simulated signal, for a 3 gig signal, with the maximum rise time, you can see that we're well within that, that maximum. However, as we go now to the higher, the faster signal, so this is now 1/10 the maximum rise time, so 22.5 picoseconds. What you can see is, first of all, that the eye pattern opens up, which is good. That means you reduce the probability of errors. And the jitter reduces. The jitter now becomes only 1.7 picoseconds. So these are two good reasons why fast line drivers are good, despite the fact that they spread more of the frequency of the signal to the higher frequencies, is that they reduce the alignment jitter, and you spend more time at the high and the low voltage, so it opens up the eye pattern. So what happens for a 12 gig signal going through the same system? Remember, this is a system that meets the SMPTE 2082 spec. Well, the eye starts to look fairly closed, and you can see quite a bit of distortion, and this is barely the slow signal. Now this is for the fast signal, and you can see again that you have a higher, more open eye, but the eye starts certainly to close. So those are parameters that we have to watch. Finally, I want to talk about long cable runs. So I did the simulation of a 207 foot of Belden 44505 run, which meets the maximum attenuation spec'd by 424, SMPTE 424, 20 dB attenuation at half the clock frequency of the 3 gig signal, and the corresponding 40 dB attenuation at half the clock frequency of the 2082. And you can see that the eye pattern is completely closed. I mean, this is the output signal, as you can barely tell there's any transitions. Now, does that mean you would not be able to receive such a signal? No, because as we demonstrated earlier, the equalizer, the adaptive equalizer at the receiver would do a good job of equalizing the signal and opening the eye pattern up for you. But only assuming, of course, that the loss were proportional to the square root of frequency, which is one of the assumptions. So that still can work because alpha is proportional, the loss per meter is proportional to the square root of frequency. So to summarize quickly, these are the challenges that we face with 12 gig operation, and these are our recommendations and mitigations, what we can do about them. So this SMPTE 2082 is fairly lax about the high amplitude reflections, and I recommend that we exceed the spec and design better systems, field better systems than the ones allowed by that. Dielectric loss does become to start important at 12 gigahertz, and we have to watch the use of PC boards and microwave substrates and use as much as possible gas-injected dielectrics. Group delay variations can cause distortions that cannot be compensated by adaptive equalization. The adaptive equalizer has no data about group delay distortions. And so how do we deal with that? Well, when design components, we minimize the impedance discontinuity, we use high-quality coax cables, and only use components that are single mode at the maximum frequency. So, and so to do that, we may in fact need to redesign some of the standard components, albeit for BNCs and mini WECOs that are very common components, only the areas where the dielectric holds the pin are the biggest offenders, the areas we would have to redesign. And finally, the standard allows for slow rise, very slow rises, but I still advocate the use of fast line drivers that exceed the standard, but we have to watch what happens to those increased reflections that are the result of those. Thank you very much. Any questions?